Okay, here's a second example from 7.2. This one's dealing with quadratics. So we're going to consider this absolute value function. We're going to determine the y and X Intercept Graph, determine the domain and range, and then express as a piecewise. Okay, so first of all, we're just going to look at the x and y. So for the y-intercept, we're going to set x equals 0. So we're going to have y is equal to 0 squared minus 3x minus 4. Oops, 3 times 0 minus 4. So I'm just plugging in zeros right here. Okay, I get 0 minus 3 times 0 is 0 minus 4. The absolute value of minus 4 is 4. So there is my y-intercept. So I have that at 0 and 4. And now let's look at my x-intercept. So I set my y is equal to 0, and then I have to solve this. Remember, we said that the absolute value of 0 had to be 0. So I know that this inside the absolute value has to equal to 0. So I'm going to factor this. I'm going to get x minus 4, x plus 1. I'm going to set each factor to be 0. So I'm going to get x equals 4 and x equals negative 1. So I have y-intercepts of 4 and 0 and negative 1 and 0. Okay, so let's put these all on the graph. I have it at 4 and 0, I have negative 1 and 0, and I have 0 and 4. Okay, so we did this. Now we need to graph the function. And the easiest way to graph this function would be to put it into intercept form. And if you remember, that is y equals a x minus h squared plus k. Okay, or did we use p's and q's? We might have used p's and q's there. Okay, they might be changing this on us. So in order to do this, we actually need to complete the square. So I'm just going to do the regular function first without the absolute values. Remember, we started with x squared minus 3x minus 4. And we need to complete the square. So what we do is we kind of look at these things right here. I didn't mean to do absolute values. And we take half of this and square it. So we go x squared minus 3x plus half of negative 3 is going to be negative 3 halves all squared. Okay? Now don't forget we have a minus 4 here, and because we added 3 halves on this side, we need to subtract it over here. So we have to go minus 3 halves squared. Okay? So the reason we did this is this now simplifies into x minus 3 over 2 all squared. And now we just have to do some work here. I'm going to write negative 4 as minus 16 over 4. And this is going to simplify into 9 quarters because I square the top and the bottom. Okay? So, did I do that right? 4 times 4 is 16. I did. Okay. So one more thing to do. I get x minus 3 halves all squared. Negative 16 minus 9 is going to be negative 25 over 4. Okay. Okay. So this tells us then that our vertex, our h is going to be, remember we said up here, we have minus h is our vertex. So we have 3 halves, even though there's a minus there. And our k is going to be, remember, it's plus k, so it's exactly what's written here. So it's negative 25 over 4. And just so you know, that's about negative 6.25. Okay? Okay, so that is the center. That is our vertex. So we're going to put our vertex on here. It's going to be at 3 halves. So x is at 3 halves. 3 halves is about here. And then we have negative 6.25. 4, 5, 6 and a quarter. So that is our vertex, x and y. Okay, Let's think about this. Is this concave up or concave down? Because our A value, our value in front right here is like a 1, that means it's vertex up. So it's basically looking like this original graph is going to be a parabola up and looks something like that. Okay? But remember, we're doing the absolute value. So the parts that we don't like are all of these parts right here. And those, in fact, are going to be reflected. So instead of being negative 6.25, let's put that at positive 6.25. 1, 2, 3, 4, 5, 6.25. And actually, this graph, as soon as it starts becoming negative, is reflected upwards. And notice that that nicely symmetrically went to that point we had there. So our real graph looks like the regular graph until it hits the x-axis. Then it becomes positive, reflected, and then where it hits 0 again, it's back to the regular graph. So this red one is what my graph really looks like. Okay, this stuff down here isn't even the graph. Okay, so we graphed this. Now we need to determine the domain and range. So let's look at the x values. I could put any x value in. So my domain is all x such that x is a member of the reals, any real number. And my y, well, it has all y values except for negatives. And the reason this could change is if your graph actually started up here, that's the only time we would say it's not what I'm writing right now. Okay, and so my domain is all y such that y is a member of the reals. Oops, all y's. I say one thing and write another. All y such that y is greater than or equal to 0. Y is a member of the reals. Okay. Now we need to do the piecewise. Okay. So the graph is just like the positive graph. Remember let's rewrite our function so we can see it. It was y is equal to the absolute value of x squared minus 3x minus 4. Okay, so remember it was like the normal graph here and there. So that's what I'm going to say. I'm going to say y is equal to, and it looks just like x squared minus 3x minus 4, so just this graph right here, whenever x is less than negative 1, whenever x is over here, and also over here, whenever x is greater than 4. Okay? But here, this part right here, whenever it's between those two things, and the way we write that is we say whenever it's between those two guys. So I say, I always read this from the outside. Whenever I say x is less than or equal to 4, but greater than or equal to negative 1, it's equal to the reflection of this graph. So I just put a negative sign in front of it like that. Okay, so that's how we deal with quadratics and absolute value functions.